Ever wondered what quantum programming is all about? Quantum programming involves designing sequences of instructions, known as quantum circuits. These circuits use gates, switches, and operators to manipulate quantum systems, aiming for specific outcomes in experiments or calculations. Now, you might be asking, how does this differ from classical programming? Well, classical programming uses bits that are either 0 or 1. Quantum programming, on the other hand, uses qubits, which can be both 0 and 1 simultaneously thanks to superposition. To express quantum algorithms, we use high-level constructs in quantum programming languages. These languages help us develop and test quantum circuits on quantum processors. The exciting part: most of this software is open source, meaning it's available for everyone to explore and contribute to. Quantum computers, like those based on the KLM protocol, leverage quantum algorithms implemented with complex electronics, integrated circuits, and sophisticated instrumentation. These systems open up new possibilities in fields like cryptography, material science, and even artificial intelligence. But it's not just about the hardware. Let's talk about quantum instruction sets. These are essential for turning higher-level algorithms into physical instructions that can be executed on quantum processors. Sometimes these instructions are specific to a given hardware platform, such as ion traps or superconducting qubits. One notable example is cQASM, also known as Common QASM. This hardware-agnostic quantum assembly language guarantees interoperability between quantum compilation and simulation tools. It was introduced by the QCA lab at TU Delft. Another significant instruction set is Quil, an architecture for quantum computing that first introduced a shared quantum classical memory model. This was brought to life by Robert Smith, Michael Curtis, and William Zeng in their work, A Practical Quantum Instruction Set Architecture. Many quantum algorithms, including quantum teleportation, quantum error correction, simulation, and optimization algorithms, require a shared memory architecture. OpenQASM is another key player. This intermediate representation was introduced by IBM for use with Qiskit and the IBM Q experience. Additionally, there's Blackbird, a quantum instruction set and intermediate representation used by Xanadu Quantum Technologies and Strawberry Fields. It's designed to represent continuous variable quantum programs that can run on photonic quantum hardware. Do you know about quantum software development kits? The following software development kits can be used to run quantum circuits on prototype quantum devices, as well as on simulators. First, we have an open source project created by Quandela for designing photonic quantum circuits and developing quantum algorithms based on Python simulations are run either on the user's own computer or on the cloud. Percival is also used to connect to Quandela's cloud-based photonic quantum processor. Next, an open-source suite of tools developed by D-Wave. Written mostly in the Python programming language, it enables users to formulate problems in Ising model and quadratic unconstrained binary optimization formats, QUBO. Results can be obtained by submitting to an online quantum computer in Leap D-Wave's real-time quantum application environment, customer-owned machines, or classical samplers. Qibo is a modular framework which includes multiple backends for quantum simulation and hardware control. Developed by multiple research laboratories including QRC, CQT, and INFN, this open-source full-stack API focuses on providing a platform-agnostic quantum hardware control framework with drivers for multiple instruments and tools for quantum calibration, characterization, and validation. Rigetti's open-source project uses the Python programming language to create and manipulate quantum circuits. Results are obtained either using simulators or prototype quantum devices provided by Rigetti. In addition to basic quantum operations, higher-level algorithms are available within the Grove package. Forest is based on the Quil instruction set. Cambridge Quantum Computing has developed a quantum programming environment and optimizing compiler that targets simulators and several quantum hardware backends. Released in December 2018, this tool provides a comprehensive suite for quantum development. Strawberry Fields, developed by Xanadu Quantum Technologies, is an open-source Python library for designing, simulating, and optimizing continuous variable (CV) quantum optical circuits. It offers 3 simulators, one in the Fock basis, one using the Gaussian formulation of quantum optics, and one using the TensorFlow machine learning library. This library also executes programs on Xanadu's quantum photonic hardware. Microsoft's contribution to the quantum ecosystem comes as part of the .NET framework. Quantum programs can be written and run within Visual Studio and VS Code using the quantum programming language Q#. Programs developed in the QDK can be run on Microsoft's Azure Quantum and executed on quantum computers from Quantinuum, IonQ, and Pascal. Lastly, Google's open-source project Cirq uses the Python programming language to create and manipulate quantum circuits. Programs written in Cirq can be run on IonQ, Pascal, Rigetti, and Alpine quantum technologies. Not the last part, quantum programming languages. There are two main groups of quantum programming languages: imperative quantum programming languages and functional quantum programming languages. Ket is an open-source embedded language designed to facilitate quantum programming, leveraging the familiar syntax and simplicity of Python. It serves as an integral component of the Ket quantum programming platform, seamlessly integrating with a Rust runtime library and a quantum simulator. Maintained by Quantiloop, the project emphasizes accessibility and versatility for researchers and developers. Quantum Computation Language, or QCL, is one of the first implemented quantum programming languages. The most important feature of QCL is the support for user-defined operators and functions. Its syntax resembles the syntax of the C programming language, and its classical data types are similar to primitive data types in C. One can combine classical code and quantum code in the same program. Quantum pseudocode, proposed by E.NIL, is the first formalized language for the description of quantum algorithms. It was introduced and, moreover, was tightly connected with a model of a quantum machine called Quantum Random Access Machine, QRAM. A language developed by Microsoft to be used with the Quantum Development Kit is the Q language. The second implemented imperative quantum programming language, Q language, was implemented as an extension of the C++ programming language. It provides classes for basic quantum operations like Q-Hadamard, Q-Fourier, Q-Anot, and Q-Swap, which are derived from the base class Q-Op. New operators can be defined using the C++ class mechanism. Quantum Guarded Command Language, QGCL, was defined by P. Zuliani in his PhD thesis. It is based on guarded command language created by Edgar Dijkstra. It can be described as a language of quantum program specification. Quantum Macro Assembler, QMASM, is a low-level language specific to quantum annealers such as the D-Wave. Scaffold is a C-like language that compiles to QASM and OpenQASM. It is built on top of the LLVM compiler infrastructure to perform optimizations on scaffold code before generating a specified instruction set. The logic of quantum programs, LQP, is a dynamic quantum logic capable of expressing important features of quantum measurements and unitary evolutions of multipartite states. It provides logical characterizations of various forms of entanglement. The logic has been used to specify and verify the correctness of various protocols in quantum computation. QFC and QPL are two closely related quantum programming languages defined by Peter Selinger. They differ only in their syntax. QFC uses a flowchart syntax, whereas QPL uses a textual syntax. These languages have classical control flow but can operate on quantum or classical data. Selinger gives a denotational semantics for these languages in a category of superoperators. Efforts are underway to develop functional programming languages for quantum computing. Functional programming languages are well suited for reasoning about programs. Examples include Selinger's QPL and the Haskell-like language QML by Altenkirch and Gratich. Higher-order quantum programming languages based on lambda calculus have been proposed by Van Tonder, Selinger, and Valeron, and by Arrighi and Diewick.